Welcome back to the Explainer. We've all had that moment, right? You stroll up to the grocery store and the doors just magically slide open for you. Or you're driving at dusk and bam, the streetlights flicker on at the exact right second. Today, we're jumping straight into the magic behind those automatic devices we literally use every single day. We are demystifying smart technology, tearing it down to the studs, and looking at the exact builder's blueprint for how physical computing actually works. And this brings us to a huge shift happening right now, the core philosophy of modern maker culture. Because of massive technological innovation, it's no longer just giant tech companies or hardcore programmers building these things. Ordinary folks, you, me, we can write programs and build smart devices. The quote here really hits the nail on the head. This turns us from mere tool users to tool builders. It's incredibly empowering. We're moving from just blindly consuming technology to actually creating it to solve real-world problems.
So here's our blueprint for today's explainer. First, from users to builders. Second, senses, brains, and actions. Third, programmable microcontrollers. Fourth, event-driven programming. Fifth, automating our world. And finally, number 6, the future, IoT and AIoT.
Let's kick things off with Section 1, from users to builders.
To make that leap from user to builder, we have to understand the fundamental logic that powers absolutely every smart device around us. The big takeaway here is the input-process-output cycle. It's the chronological heartbeat of data flowing through any electronic device. First up is input, which is just the raw data the device pulls in from the physical world. Next is process, where the device analyzes that data using specific rules. And finally, output, the actual physical response the device gives back. Honestly, if you can wrap your head around this simple 3-step loop, you can understand how literally any robot or smart home gadget functions.
Moving right along, Section 2, senses, brains, and actions. To truly grasp how this input-process-output cycle works in the physical world, let's get into the hardware. Think of sensors as the actual senses of a device. They automatically read physical quantities from the world around them. So a light sensor? It measures light intensity, which is how automatic lighting knows when to turn on. An ultrasonic sensor bounces sound waves to measure distance. That's what's beeping when you back up your car. Temperature sensors manage climate control, and a PIR, or passive infrared sensor, picks up human movement. That's the secret behind those automatic doors we mentioned earlier. It's pretty fascinating when you see the actual raw materials that capture all this input data. You've got these tiny electronic modules doing all the heavy lifting. Some of them even look a bit like a pair of robotic eyes. But along with these automatic sensors, we also use manual input devices, things like buttons, joysticks, or slide potentiometers. These are the inputs where we physically hand the data over ourselves. Okay, so once that data is gathered and processed, the device needs an output. It needs a voice or a muscle to actually interact with the real world again. These outputs come in all shapes and sizes. You've got LEDs to emit light, buzzers sounding alarms, digital displays showing dashboards, and DC or servo motors providing actual physical motion, like spinning a cooling fan or moving a robotic arm to a highly precise angle. Which brings us to Section 3, programmable microcontrollers. Right, so we have our sensors gathering data and our motors waiting to move. But how do we actually connect those senses to those muscles? Well, that is where the brain of the operation steps in, the programmable microcontroller. Think of it as the ultimate traffic cop. Basically, it's a small circuit board packed with various ports and pins. These pins let you easily hook up all those different input and output devices we just talked about. Once everything is wired up, this tiny board executes tasks based on the specific software program you upload to it. So how does that combination physically work in practice? Well, you take your hardware part, the physical input sensor reading the environment, and that sends a signal straight to the microcontroller in the middle. The microcontroller then runs your uploaded software program, makes a decision, and fires a signal over to the output device. It's a perfect partnership. The hardware is the physical body, and the software provides the brains and the instructions. Now, if the idea of writing software instructions from scratch sounds a little intimidating, don't worry. There are different ways to do this. You can use visual block-based programming, where you literally just snap together colorful command blocks like puzzle pieces. Or you can use traditional textual programming, typing out code in a language like Python. The awesome thing is, both methods achieve the exact same result, like programming an LED screen to show a beating heart. Visual programming is just a fantastic way for beginners to nail down the logic without getting tangled up in complex syntax. All right, Section 4, event-driven programming. We have our coding environment ready, but we still need to set the specific rules for our device to follow. In the real world, most electronics don't just do tasks randomly. They wait for a reason to act. We call this event-driven programming. It's basically a design where we tell the microcontroller, hey, wait for this very specific trigger. Once that specified event happens, and literally only then, the corresponding code is finally executed. This isn't some abstract computer science concept either. We see this every single day. Think about it. When you physically press the shutter button on a digital camera, that specific event triggers the code to capture a photo. When you press the call button for an elevator, that event triggers the motor to bring the lift to your floor. And yeah, even if you impatiently mash that button 10 times, it's still just one trigger event translating into code. It's simple cause and effect. Next up, Section 5, automating our world. Let's see how this scales up from simple button presses into sophisticated systems that seem to think entirely for themselves. To ground these coding concepts in our daily reality, let's ask a really simple question. Why exactly do doors open automatically when we walk near them? Or, why do public sinks dispense water without us ever turning a handle? The magic word here is automation. Automation is what allows a computer to make decisions completely on its own, based entirely on a preset program we wrote beforehand. So when that PIR sensor detects the event of someone walking past, the program checks its conditions and automatically tells the motor to slide the doors open. This reduces manual work, runs 24/7 without getting tired, and massively improves efficiency. If we map out the logic for something like a smart streetlight, we can clearly see that input-process-output cycle looping continuously. The program reads the value from a light sensor and asks itself a question. Is the brightness out there less than our threshold? If the answer is no, it loops back around and keeps the LED off. But if the answer is yes, meaning the sun has finally set, it triggers the output and turns the LED on. It is an endless, highly efficient, automated decision-making loop. And finally, Section 6, the future, IoT and AIoT. Here is where things get truly massive. Because what happens when we scale these individual automated loops up and connect them to the rest of the world? Well, if you take a smart sensor and connect it to Wi-Fi, you get the Internet of Things, or IoT. This is a massive network where objects transfer data to one another over the internet. But it gets even better. When we integrate artificial intelligence and big data to analyze all that gathered sensor information, we unlock AIoT, the artificial intelligence of things. Suddenly, the AI can analyze massive trends and take highly complex autonomous actions without us lifting a finger. Imagine how this comes together in a fully integrated smart home ecosystem. That smart air conditioner on your wall, it isn't just reading a room thermometer anymore. Through IoT, it's talking to the GPS on your smartphone. It detects that you're just a few miles away, heading home, and automatically turns itself on so you walk straight into a perfectly cooled living room. And looking to the future, AIoT is going to scale up into some truly visionary living spaces. We're talking about smart mirrors that pull real-time weather data from the internet to automatically suggest an outfit for the day. Robot vacuums that don't just clean but map and sterilize your house while you sleep. Or think about a smart emergency system that uses sensors to detect if an elderly person takes a fall, autonomously calling emergency services for help without a single button ever being pressed. It's an absolute game changer. We've journeyed all the way from basic inputs and outputs to global AI-driven networks. You are no longer just a passive consumer of these magical devices. You actually know how the magic trick is done. So I want to leave you with this. Now that you understand the builder's blueprint and you know how physical computing actually works, what real-world problem are you going to solve? What are you going to build next? Thanks for hanging out with us on this explainer. Keep learning, and most importantly, keep building.